Okay, so today I want to define one of the main objects of this lecture, the Yangian. The Yangian, which corresponds to the general linear Lie algebra. This is my notation. So the idea is as follows. Let me give first some informal definition, not rigorous, and then I will proceed to a detailed exposition. So the first definition looks as follows. Our object is an associative algebra over the field of complex numbers, which is defined as follows. First, we take infinitely many generators, which are denoted as follows. Here, the lower indices are from 1 to n, and m takes the values 1, 2, 3, and so on. Of course, this is a free algebra, but we take a quotient modulo some relations. Some relations to be defined shortly. And the properties are as follows. Let me recall the definition of a matrix, which I will denote as follows. This is the matrix which is formed from the matrix units. So these are my matrix units. So this is an n by n matrix. And next we take its power m and take the entries ij. And these are defined as follows, as a multiple sum from indices A. I'm sorry. Excuse me. And I will denote it as follows. And this is an element of the enveloping algebra. And it's convenient to add one extra index n here. And the idea is as follows. For any n prime, which is greater or equal to n, there exists a homomorphism of our Yangian to the enveloping algebra such that our generators are mapped into these elements in prime. Okay. Here I J ranges from 1 to n, but n prime may be arbitrarily large. And moreover, one can prove the intersections of the kernels of these maps is 0. So in some sense, one can say that our relations to be defined are satisfied by these elements. But it's difficult to see this directly. And I will, another way is to say as follows. These elements satisfy some commutation relations which are stable in the sense that the form of these relations does not depend on this n. But of course, this map has some non-trivial kernel. But it turns out that, as roughly speaking, as this number gets large, in a certain sense, these kernels get smaller, smaller, and smaller. And one can say in a certain limit, it becomes 0. So one can say that a Yangian arises in a certain way from the universal enveloping algebra via some non-trivial limit transition. But now let me proceed to a detailed exposition. So I have to define the relations. And these relations are as follows. It takes the following form. So I need one more convention. It is convenient to set, this is the scalar, the Kronecker delta. Let's keep this convention. I will use it many times. And now I will write down the commutation relations, the defining, let's say, defining relations. Definition. The defining relations of the Yangian are as follows. I will write it. This is the left-hand side, and on the right, you see we have and here I recall this notation, and M, L take these values. So in particular, if say L is equal to 0, then this is a scalar. And so this commutator is 0, but we have this one. So we have infinitely many generators and infinitely many defining relations. Of course, this may look a little bit strange, but let's see what happens next. I will rewrite step by step this relation, and finally they will appear in a very compact form, very convenient for working with these relations. The idea is to use generating series. So the next topic is some special generating series. Generating series to be used. So assume that we have some algebra. general setting, some algebra. And where is a sequence? Assume we are given an infinite sequence of elements. This algebra, and we want to combine them into a generating series, but the usual way to do this is to take a formal power series. But for some reason, it's not convenient for us. And I will use instead a little bit different form of a generating series as follows. I will use here capital M, and here I will write as follows. So this is a formal power series in inverse powers. So this object is an element of this algebra. Why? One of the reasons is that for formal power series of this type, in contrast to this one, it's possible to define, so let me denote it. Introduce notation A of U. So given a sequence like this, I want to consider this object for an element of this algebra. The idea is that one of the reasons why this and not so the reason is follows. This operation makes sense if C is a scalar. We can switch our formal element by a constant. If we do this in formal power series, this operation is not defined. The reason is if you re-expand a series of such type, if you want to re-expand, so write something like this, and re-expand, then the terms of lower degree will accumulate to infinity, and this operation makes no sense. But in this situation, the terms will accumulate near infinity, and this operation makes sense, indeed. So what we have, by very definition, we have something like this. And we have to re-expand. So we need to re-expand this quantity. And we use the binomial theorem. So we can write it as follows. And here we have a quantity like this. And I use the notation this is the Pohammer symbol, M times. So because of this shift, this double sum is well defined as a formal series. So keep this remark and proceed further. So let's denote this. This is a collection of defining relations. The next step is to use the generating series. I defined it as follows.
Grigory Osifovich, sorry, should we have in the expansion programmer from C instead of M?
Yes, of course. I'm sorry. I'm sorry. This was absolutely stupid. Thank you. I was lost. C, of course. Thank you. Okay. So this is my generating series. And the superscript M disappears. It is replaced by these formal variables. And I can rewrite my defining relation, rewrite. We can rewrite as follows. So let me explain what does this mean. First of all, in what algebra we are working here, and by both sides of this relation are elements of what? Both sides are elements of the algebra. Our object. Next, we take formal power series. So the left-hand side is already in this algebra. The right-hand side, not exactly, but we have to localize. Localize with respect to a multiplicative system, which is U minus V. So we want to have a possibility to divide by this quantity. This is possible because there are no zero divisors in the algebra formal power series, so we can do it. Or if you want, one can take the quotient field, but it's too large. So this is some minor issue. So we claim, so this makes sense. This makes sense. And how to see that this form, which is more compact, because there are only finitely many relations here, and squares, and sorry, not squares, relations, but finitely many, because the upper indices disappeared from our play. How to see that this is the same? This is easy. Just multiply by this, and maybe one more remark, I'm sorry, to localize, because we are using these variables and not u and v, but it's easy to see because one can write minus v is something like this. So actually we can localize with respect to these quantities and not with this, because formally these elements do not belong to our algebra, but these elements are elements of the algebra. Okay, so multiply. So let's multiply by this to proof. So multiply by u minus v and compare the coefficients of.
I'm sorry, I think your fraction above is wrong because it's equal to 1, no? I mean, on the right-hand side.
Yes, of course. Thank you. Thank you. So the idea is to multiply by this quantity, and look at the coefficients of this monomial, and we see that we get exactly our relation. Okay, so this is the end of the proof. But let's go further. Turns out that it is possible to write all this system of relations. One can pack it into a single relation, but in a matrix form. So the matrix, so-called RTT relation. It looks as follows. We introduce the T matrix. T looks as follows. And so on. So we combine all these elements into a single matrix. And what it is? It's an element of the algebra of matrices with entries in our algebra. And this is also can be written as the following object. I'm sorry, there are hidden formal variables here. So more rigorously, it is an element of the algebra and formal power series with coefficients in this algebra. So this is an element of this big object. But actually, I need something more. I need not only Cn, but the tensor product of two copies of this space. And I introduce the R matrix, so-called Yang R matrix, which is an element of a space of operators in this tensor product. So this is a matrix of size n squares times n squares. But it's more convenient to regard it as an operator. The definition is as follows. First, I need another matrix P, which is simply the very natural operator, which permutes the factors in this tensor product. And it can be written as the sum like this in terms of a matrix units. And indeed, if we consider the action acting on, say, these are the basis elements, we see immediately that the effect of this action is just the flip, the permutations. And finally, the R matrix is defined as follows. So this is an element, an operator acting on this space. And
I'm sorry, U is a formal parameter here?
Yes.
So it should be of U also. I mean, R is from endomorphism, or should we add U here?
Yes. You are right. Thank you. It's correct. It's correct. Without tensor.
Not on P, on R, I think.
Mm-hmm. Mm-hmm. Thank you. Okay. I need something more. I will call it also matrices, but they are maybe not exactly matrices, some objects, some elements, which live in this big object. And they are defined as follows. T1 is by definition the sum and T2 is something similar. How to understand this? Let's imagine. So I like the following way of explanation. For convenience, let's imagine that Y is realized inside some algebra of operators on some space W. For instance, we can always take the regular representation of the algebra on itself. So the nature of this space is irrelevant. And let's set V is here. So actually, we have the triple tensor product of spaces W, V, and V. And T1 operates on this space and acts trivially on this tensor product. And T2 operates on this space and acts trivially on this copy. Is it clear or not? Because this is a very important step. So you need to understand clearly what happens here. So please ask some questions. Is it clear? Okay, so I will continue.
The realization inside endomorphism is clear, but I'm a bit lost in the original definition. So Tij of u live inside Y tens. No.
Let me explain. Okay, so T1 and T2 live in this object. Let's neglect the formal parameters. It can be added without problems. But here we need to distinguish the copies of V. So actually T1 lives in this space. And T2 lives in this space. Okay. But now we embed both these into. No, it's impossible to do. The spaces cannot be embedded, but the endomorphism algebra can be embedded. So one can write that and is contained well, this is correct because the spaces V are finite dimensional. We simply assume that the action of this object, this algebra, is trivial on this tensor component. And likewise, we have the embedding in the same space. And now we can embed both this element, which is here, we can embed it into this. And likewise for this. Is it clear now?
Yes, thank you.
Okay, thank you. This is important. So don't hesitate to ask me if something is not absolutely clear. And now the claim is as follows. Let's write this theorem. The defining relations are equivalent to a single relation, which is the following. This is the famous triple or RTT relation. It's more complicated, but it is a single relation, and this is why it is very useful, extremely useful, I would say. Let's prove this. Why this is equivalent to our initial relations. The proof is not difficult, but let me give it. So let's write the left-hand side and the right-hand side. We have the sum over I, J, K, L. This is the left-hand side. Is it clear or not? Because this and this is this one, T1, and T2 is obtained from these two terms. Okay. So this is the left-hand side. And what is this object? Because the T generators and all that happens in this space commute, so actually we can put it here. So this object together with this is an operator on the tensor product of two copies of our space V, Cn, and dimensional space. Okay? So one can put it here. But on the right, we have something similar. Summation. 1 to n. And what we get? Why this is correct? Again, please look. So this is this object, T2, and this is T1. The order corresponds to this order. We don't permute this here because T2 is associated to the second copy of our space. Okay? So this is correct. And again, this object is an operator in our tensor product, in our double tensor product. Okay? Now let's transform. Let's transform this. This is equivalent. This is equivalent to the following relation. Again, we have this multiple sum. What I do, I want to put this term associated with this on the left-hand side. And the terms containing P, I put them on the right-hand side. So on the left, we get this. This is the left-hand side. And the right-hand side is as follows. This is because I take into account the possibility to move it here. Okay? And a similar expression. But P is on the right, because it is on the right here. But now we remark the following. What is P multiplied by these operators? All this is an element in this space. It's easy to see. I'm sorry, it's incorrect. The action of P on the left results in transposition of these indices. We have a flip of these indices, so we get Kj, this one. So we have to substitute, this, substitute here, substitute, and likewise, multiplied by P results in the flip of these indices. So this is nothing else but this. Now we substitute here. But then we get almost what we want. The only point, the final point, is to change the notation, maybe it's better to say not change, but rename the indices. We have summation. Here. So we can rename these indices as we want. So now we rename these indices so we can keep this notation, but we have to rename this. So k is written inside instead of I and vice versa. And here we have the same point. We have to rename these indices. So this is again J and this is L. And we get the second form of our relation. What we get? We get this one, exactly this one. So this is the end of the proof. Some questions maybe? Is it okay? Well, let's proceed next. Proof. Some corollaries. The first corollary that we have the so-called shift automorphisms. There are the shift automorphisms of a Yangian, that denoted by sigma C. The parameter C is an arbitrary complex number. So we have an algebra automorphisms. Which is defined as formally as this map. What does this mean? This means as follows. We have to specialize the image. Toward. The idea is as follows. To write and these are the coefficients of the entries of the matrix T tilde, which is by definition this one. So this is another matrix, and it's possible. The definition is correct because this shift of a formal argument is well-defined operation. So we look at the entries. So this gives us, This gives us the indices, and we consider the coefficients which arise from the expansion, from re-expansion of this formal power series. And it's easy to see that this is an automorphism, it is invertible, so no problem. So we see that the additive group of a complex number acts in a certain way by automorphisms of our algebra. It's not so surprising because our algebra is very large, and there is some action. Okay.
I'm sorry. It is an automorphism because our matrix depends on.
Yes, exactly. I'm sorry. Yes. Excuse me. I have to explain. Thank you. I skipped erroneously this. So the explanation is as follows. So look at this RTT relation. If we substitute U plus C, V plus C, the relation remains intact because the difference U minus V does not depend on this shift. So we can insert here U plus C. Thank you. Excuse me, I forgot to say this. Is it clear? Okay. Okay. What next? There is a less trivial automorphism, which I call inversion. The inversion automorphism. It is defined as follows. It takes this matrix, our matrix, to this matrix. Why it's correct? It's correct because, okay, so the change of the sign is something quite trivial. We use the fact that our matrix T of U has the term 1 plus something, which can be written as follows. So, and such a matrix is invertible because the constant term is 1. Is it okay? No questions. And what is the interpretation of this definition? This definition is the same as here. We can proclaim this object as a T tilde, expand on the series, take the coefficients and say that these coefficients are the image of our generators. So this is the definition. Now we have to see, to check that our RTT relation is preserved under this operation. So let's check. Let's check. It's easy. Indeed, what we have to prove? We have to prove the relation. We have to prove the following relation. Now we want to get rid of the inverse inverses of this matrix. So this is easy. So let's multiply on the left. Multiply on the left by these quantities. Sorry, I missed. And on the right by these quantities. And then we obtain the following. Okay. So let's Let's rewrite it. So put the right-hand side on the left and vice versa. So we have okay. And now we can rename the formal variables. This gives us U renamed by minus V and V renamed by minus U. And this gives us so it's almost we want. The only problem is that we want to have one, not two, and two instead of one. How to do this? Finally, conjugate by P. It's invertible, P. So because P squares is equal to 1. And the conjugation by P produces the operation we need. So 1 and 2 are replaced. So we get what we want. So we see some very primitive computation. What next? Some play with our formal relation. Next topic is some proposition. Let me call it proposition. The truncation map. The claim is as follows, that consider the map. This is our initial matrix, which is formed from the matrix units. Consider this map, which means that, and this is an element of our enveloping algebra. Okay, this is actually something simple, but it is contained here. So what is this? This means that we have a map which assigns to our generators, psi assigns to it what? The matrix unit, if M is equal to 1 or 0, otherwise. So we kill all the higher elements Tij with upper index not equal to 1, 2, 3, and so on are killed. So we claim that this is an algebra morphism. So that is, which means that is satisfied. This is a little exercise. Let me leave it as a home work problem. Why I will use this. Now The theorem is as follows. Let's denote by psi tilde. Maybe I will put the index n here. You will see why. This is a map from our algebra to the universal enveloping algebra, which is defined as follows. Is by definition our elements. So I claim theorem as follows. Is an algebra homomorphism. So this means that our elements, these elements, satisfy our defining quadratic relation. How to do this directly, I don't know. But it's easy to do using the R matrix formalism. So I present now the proof. The idea is very simple. I claim that this psi tilde is equal to the superposition, meaning that we take first this automorphism and the truncation. So if you check this claim, this equality, then we get our claim, because this is an automorphism, this is a morphism, so we get it. How to check this? It's easy. Why? Because we have, I recall that we have T of u is 1 plus where Tm is by definition the matrix which is composed from our generators with capital M fixed, and these are the indices for our entries. So what you have? First of all, we have to apply the inversion. So we have this one. It is mapped to, which means that we take this matrix. Minus 1. But then we have to kill all Tm if m greater or equal to 2. So we get simply And this is the same, because this is exactly our matrix composed from the matrix units. So this is the same as and what is this? So this is 1 plus okay. So if you want to take which is same as you have to take these entries, this entry, and extract the coefficient. The extraction is in combinatorics is written usually in this way. This means that we have something which is a formal power series, and we extract the needed coefficient. But this is the same from our result. This is the same as extracting the coefficient, extract from this. This is exactly what we get is this, because this is equal to and that's all. So we see that there is a powerful formalism which enables us to work with the defining relations. Some questions, maybe? Okay.
Will we get something interesting if we take, instead of inversion, some translation?
I have to think. It's not so interesting, but yes, there is something. But yes, it's important. It's important also. It's important also, but this procedure is more useful. But all combinations in some situation, all combinations, there are other automorphisms. I don't want to discuss it just now. And there are various automorphisms and various combinations, and the whole play with these objects makes sense in such in some situations.
Okay, thank you.
There are plenty of tricks related to this material. But now I still have some time. I want to discuss the next topic. This is the Poincaré-Birkhoff-Witt. Poincaré-Birkhoff-Witt type, let's say, theorem for our Yangians. What is this? First of all, let's introduce the filtration. Filtration in the Yangian, which is defined as follows. We proclaim that the degree of the generators is by definition is equal to m, which is quite natural because we see that it is related to our element of this type. And these are, as elements of a universal undeveloped algebra, they have degree m. So we put it here. And so we define a filtration in the usual way that the mth term of a filtration is obtained by taking arbitrary products of the generators, assuming that the degree is given by this definition. So what we get, taking the sum, we get the term number m of our filtration. And the claim now is, that the associated algebra is commutative. Again, this is quite natural to see, to assume, because the same happens in the universal undeveloped algebra, but let's prove it. Let's prove it. The idea is as follows. We have our initial relations. I recall them. Let's return. But write it as follows. And plus some what was on the right-hand side, but I don't want to write in detail. The idea is this: these are lower degree terms, because the degree on the left is m plus l plus 1, and these terms have degree m plus l. So they are lower degree. So we can see, let's rewrite it as follows. So this element is, let's say, equal to this one, modulo the lower degree terms, and continue this. So this is congruent to Tij m minus 1. So look at the structure. And here we have, and so on and so on. And finally, we arrive to Tij 0. And here we have T equal L, m plus L plus 1, but this is a scalar, so this is 0. So the result is that the commutator is 0 modulo this subspace. So this is inside plus 1, and this is this component. So this is just means commutativity. This just means commutativity. We can replace m plus 1 by m, rename it, and we get commutativity. So this is commutative. So the claim now, theorem, is as follows. The graded algebra is isomorphic. To the algebra of polynomials in I need to rename my generators, say in generators, PIJM. So in my definition, PIJM is the top degree term. Top degree term. So this is an element of which is the mth homogeneous component of this gradient algebra. So what we get? We get the same type of result as in envelope algebra. In the envelope algebra, we take the basis in the Lie algebra, we take non-commutative polynomials, and the claim of the Poincaré-Bergov fit is that the associated gradient algebra is the algebra of polynomials, the symmetric algebra. Here the situation is the same. The difference is only that in the classical case, the elements of Lie algebras have degree 1. And here the generators have can have arbitrary large degree, but this does not matter. The claim of Poincaré-Bergov fit still makes sense. And also another difference is that we have infinitely many generators, but again, no problem with this. So how to prove this? How to prove this? And the proof goes as follows. Proof goes as follows. First of all, the first step is as follows. This is just an observation that assume that n prime is greater than n, then we have an algebra morphism which is simply the Tijm goes to Tijm. But here, this element is algebra, and this element is here. One could use more detailed notation, namely to write something like this. At one extra index. Now, in this notation, the map is as follows. In prime. So why this is an algebra morphism? But it's evident because our initial defining relations are local. They use only I, J, K, L. So no matter if these indices are subject to the relation J, K, L, or if we take n prime instead of n, nothing changes. So this means that we have such maps, which are algebra homomorphism. Okay, I would like to ask if it's clear. So the existence of this map is guaranteed by the locality, the local form of our relations. Next, what we do next? We use the following. Take a composition and next we take this map, which lives in this algebra. Okay. So this means that our generators, let's use this notation, are mapped into but the sum is from 1 to n prime. Which is something in this developing algebra. And this is an algebra homomorphism, because this is homomorphism and this is homomorphism. And it preserves a filtration. So what we get a corresponding map for this universal developing algebra. But this is the symmetric algebra. And the claim is as follows. Now the claim is as follows. Claim. Fix any natural number m bar and assume m ranges over so we restrict the possible range for the index m. So we get finitely many indices. So we claim that the elements J, M, and prime, which are viewed as elements of a symmetric algebras, which is commutative. So we have this restriction and this restriction. So we have finitely many, namely n squared times elements. And the claim is that these elements are algebraically independent. Independence as n prime is large enough. So this is some liberation effect. We have these elements, which elements? These elements. they algebraically dependent. There are some very complicated relations. But if you restrict the range of M and take n prime large enough, so the sum is large enough because the range grows, there is some liberation, so our elements become algebraically independent. So it's evident, I think, that our Poincaré-Bergouin type theorem is a consequence of his claim. So we only need to prove this, but let me postpone this for the next lecture. And I would like to stop at this point. And this is the Poincaré-Bergouin, a very important result because it gives us some, what I would like to say. We have here some effect of simplification. Inside the universal enveloping algebra, I repeat, our elements satisfy some mysterious relations, but after the transition to the Yangian gives us algebraic independence. So, okay, let me stop at this moment. I want to switch off